Thank you for the introduction, and welcome to my talk. This is a joint work with Maverick Wu and David Brumley. Today, I'm going to talk about my research about mutational fuzzing. Mutational fuzzing is an effective software testing technique for finding security bugs in COTS software, such as follows. We often call this technique as black box mutational fuzzing because we consider the program as a black box, which means we do not look at the internals of the program. The way it works is to iteratively run this program with a series of different inputs and observe the outputs. And if the program crashes, then we know that the corresponding input is buggy input. We say mutational fuzzing because we generate test inputs by mutating a given seed, which is typically a well-structured input. As you can imagine, the effectiveness of fuzzing largely depends on how we generate those test inputs, because some inputs may trigger lots of software bugs, whereas some other bugs may not. Therefore, in this project, our goal is to generate test inputs from a seed in such a way that maximizes the number of bugs found for a given limited resources. For example, one of our previous works in this line of research showed that selecting good seeds matters. By selecting a good seed, we can generate a good set of test inputs. Therefore, that triggers lots of software bugs. And similarly, selecting a good mutation strategy also matters. Given the same seed, different mutation strategies will result in different sets of test inputs. Therefore, it is a common practice for mutational fuzzers to employ various different mutation strategies based on their own heuristics. For example, AFL, which is the state-of-the-art mutational fuzzer, uses 20 different mutation strategies. BFF and ZZub, which are also very popular mutational fuzzers, they employ their own mutation strategies. However, if you notice that all these different mutational fuzzers use the exact same common bit strategy from bit flipping. The bit flipping based mutation strategy is very simple yet popular technique. The idea is to take a seed and generate test inputs by flipping several bit positions from the seed. Although it looks very simple, it is surprisingly effective in practice, and therefore it is used by many practical fuzzers, as I mentioned. However, there is one issue in using this particular strategy. Namely, we need to know how many bit positions from the seed to flip. This is important because we will get totally different sets of test inputs by flipping different numbers of bits of the seed. In fact, several mutational fuzzers even employ an additional parameter called mutation ratio to control this particular number. So in this case, the question becomes which mutation ratio should we use to generate test inputs? There are several previous approaches to tackle this challenge. The first approach is to try several different mutation ratios first to learn which ratio works best. But as you can imagine, this approach requires lots of unnecessary trials, and the selection of different mutation ratios to try is based on arbitrary decision. The second approach is to use a single mutation ratio regardless of the program under test, which may work for some programs, but this is not a general approach because good mutation ratios differ for different programs. In this project, we propose a novel approach that tackles both of these problems by directly inferring a good mutation ratio for a given program and a seed. Therefore, our approach does not require any learning process, and it is program adaptive. At a high level, our system, called SymFuzz, derives a mutation ratio from a white box analysis, and we use this mutation ratio to run classic black box mutational fuzzing to find bugs. So the key challenge here is to infer a good mutation ratio, R, from the white box analysis. In our system, we perform a three-step approach to tackle this challenge. The first step is to construct a formula representing the fuzzing efficiency, which is the probability of seeing crashing inputs. We start from the following observation. Crashing inputs derived from the same seed share some common patterns. So suppose we're given a PNG file as a seed. Since this is a well-structured input, this file consists of several data fields, as you can see here. And we're going to use a red rectangle here to represent a bit position that is flipped from the seed. And by flipping several bit positions of the seed, we can generate test inputs as follows. And out of those 4 test cases that we generated, we assume that only 2 of them are crashing inputs. And from these test inputs, we observe the following patterns. First, the 2 crashing inputs have the same flipped bit positions. In fact, there is only one common bit position that is flipped in both crashing inputs. And if you look at the 3rd test case that we generated, we generate this input by flipping just 1 bit, which means this particular bit position is really critical to find the crashing input. However, when you look at the last test case that we generated, this input also has exactly the same flipped bit position, but this input does not crash the program. The reason is because there are other bit positions that must not be flipped to trigger the crash. For example, in this particular case, we flipped a bit from the magic value of the PNG. And since we modify the magic value of the PNG file, no matter what value you have in this input will be rejected from the program because the program will think that this is not a valid PNG file. From these observations, we notice that there are 2 kinds of critical bit positions. There are bit positions that must be flipped in order to trigger the crash, which we call minimum buggy bit set. And we use small b to denote the cardinality of this bit set. The second kind is the bits that must not be flipped. And we are going to use small e to denote the number of bits that must not be flipped. And since both b bits and e bits are critical to trigger the crash, we're going to define the number of crash critical bits d, which is essentially b plus e. We also use n to denote the total number of bit positions of the seed, and use r to denote the mutation ratio. And in our model, our mutational fuzzer will generate test inputs by flipping n times r different bit positions from the seed. Now, using all these previous definitions and model, we can now define the fuzzing efficiency, which is the probability of seeing crashing inputs from mutational fuzzing. In fact, this probability follows a classic multivariate hypergeometric distribution, which essentially represent the number of attainable crashing inputs divided by the number of all possible test cases. Now that we formulated the fuzzing efficiency, we need to perform the second step, which is to represent an optimal mutation ratio with respect to B and D. In fact, we can achieve this by modeling the problem with NLP, nonlinear programming problem, where the goal is to maximize the fuzzing efficiency subject to some reality constraints. And by solving this NLP problem, we can derive the following formula representing an optimal mutation ratio R with respect to B, D, and N. And since N is known from the seed, we only need to estimate the value of B and D. Unfortunately, though, the values of B and D are not known prior to fuzzing because they are specific to a bug in a specific program. So we need to somehow estimate these values from the program under test, which is the last step of our approach. We want to estimate these values to infer a good mutation ratio for a given program and a seed. Recall from the previous example, I showed you that there are 2 kinds of critical bit positions. There are bits that must be flipped, and there are bits that must not be flipped. We notice that there is a certain relationship between these 2 kinds of bits. If we let the 2 kinds of bits as x and y respectively, then we know that there must be a control flow that checks the value of x as follows. And depending on the values of x, the program should either crash or not. And since the value of y also affects the program crash here, there must be another conditional that checks the value of y. We typically say the second conditional statement here is control dependent on the first conditional statement. And we generalize this notion of control dependence to represent the dependence relationship between input bit positions. In this example, x is dependent on the position y because the value of y determines whether the value of x will be read in the second conditional. We call such a relationship as input bit dependence, and we formally define this concept in our paper. We can compute input bit dependence of a program execution using our white box analysis as follows. First, we instrument a program execution. And for every program expression in the execution, we compute a set of relevant input bits. And finally, for every conditional branch that we encounter during the execution, we statically expand a control flow graph to compute the dependence between the input bit positions. Input bit dependence allows us to compute the number of critical bits d of any bit in a seed, which led us to define the average value of d over all possible subsets of input bits. And we are going to denote it as d bar. And notice here that we can compute this average d bar without even knowing the actual minimum buggy bit sets. So in this paper, we use the following heuristics that estimates the value of d with the multiplication of average d bar and b. This heuristic assumes the value of d linearly depends on the value of b, and this allows us to simplify the formula as follows. And therefore, all we need to do here is to compute the d bar from our white box analysis and estimate a good mutation ratio for a given program and a seed. To evaluate our system, we obtained eight applications from one of our previous works. And we fuzzed these applications for 8,000 hours of CPU time. More specifically, we used 1,000 different mutation ratios ranging from 0.001 to 1 to collect ground truth data. And in this paper, we report the number of bugs found after triaging crashes with our technique called safe stack hash, which is similar to the heuristic based on stack hash technique. For more details, please refer to our paper. The collected ground truth for the program ABCM2PS looks as follows. The x-axis here is 1,000 different mutation ratios, and y-axis here is the number of bugs found for each different mutation ratio. And you can see that there is a clear trend for fuzzing efficiency depending on the value of mutation ratio. So the first question that we want to answer is how close are mutation ratios obtained from SymFuzz compared to empirically optimal mutation ratios? So these graphs show the comparison. The dashed line here indicate the ratios derived from SymFuzz, and the blue lines here show the ground truth for each of different programs. As you can see, the prediction and the empirical was close. And this is also the case for other programs, and we also observe the similar trend in this case. As a result, the average difference between ratios obtained by SymFuzz and empirical optimal ratio was just 0.017. Now we're going to compare our system against BFF and ZZUB, which are famous mutational fuzzers. We ran fuzzing for 1 hour each of the programs and computed the number of bugs found. The red bar here represents SymFuzz, and as you can see, it prevails other fuzzers in most cases. In total, SymFuzz found 37.2% more bugs than BFF and 55.3% more bugs than ZZUB. Finally, we also applied our technique to AFL. Again, AFL is the state-of-the-art mutational fuzzer. And in order to do this experiment, we replaced bit-flipping-based mutation algorithm of AFL with our own algorithm, with our SymFuzz's own algorithm, and ran both original AFL and modified AFL for 24 hours. First, we tested the code coverage difference between the two. So the red line here shows represent the modified AFL, and the blue line shows the code coverage for unmodified AFL. And as you can see, the code coverage of our modified AFL was improved compared to the original AFL. The second comparison that we performed is the number of bugs found for both cases. And as a result, modified AFL found 18.5% more bugs than original AFL, and we conclude that our technique can also improve the state-of-the-art mutational fuzzers. There are many more details that I could not discuss due to the time limit, so please refer to our paper if you are interested. And finally, we also open our source code to boost future researchers, so please refer to our paper for more details. In conclusion, we showed that selecting a good mutation ratio is crucial in mutational fuzzing. And as a result, we devised an algorithm to leverage a white box analysis to estimate a good parameter, which is mutation ratio for black box mutational fuzzing. With that, thank you very much, and I'm happy to take any answers.
So thanks, Kil. We have time for a couple questions.
Hello. Julien Vanek from Bloomberg. I wonder if you try to combine your work with automated exploitation.
My work with?
Like automated exploitation. For example, whether you know how many bugs you found were actually exploitable, how many were null pointer references, etc.
That's a very good question. So the question was, did I apply our automatic exploit generation technique for along with this line of work? Actually, we did not try it, but it's a very good idea, and this is going to be a very interesting future work.
Yeah. Thank you.
Yes?
Hi, I'm Jonas from EPFL. There's one thing I didn't understand, and it's you seem to kind of throw away a lot of the data that you find in that you identify all these bits that the fuzzer should not change, and then you say, okay, we don't use that data, we just like count the bits. But what would happen if you actually sort of prevented the fuzzer from changing all these data-dependent bits and only like fuzz the other ones?
Right. So I think the question is, why don't we try to find a specific position of a seed that we want to modify and we don't want to modify?
Yes, exactly. Yeah.
Right. So, I mean, that's a very, very interesting question, and it's a very interesting direction as well. And actually, if you think about it, if you think about grammar-based fuzzing, usually people came up with a template that says, hey, we want to fuzz this particular part, and this, the type of this is integer, and this is a string, and so on and so forth. So automatically finding those kind of template is also very interesting research, and potentially we can extend this work to handle this case. But currently, we do not handle that case. Our model only consider the bit flipping based mutation strategy.
Okay, thank you.
Yeah.
So Juan Caballero from India Software Institute. So following on that you just answered, right? I mean, so there is years of research saying mutational fuzzing, it just doesn't get deep enough into the programs, right? So we propose things like grammar-based fuzzing, right? And that's actually widely used.
Right.
We have things like concolic fuzzing, but here you're only comparing like to the basic mutational fuzzing, and that doesn't seem like a very fair comparison. So.
Sure. So, well, you can say that grammar-based fuzzing can find more deep bugs than bit flipping based fuzzing. But actually, if you look at the bugs, the crashes that we found, actually we tried all regular file parsers, like MP3 file, GIF file, which doesn't make sense that we have without grammar-based fuzzing, and by just flipping some bit positions, how can you find crashes? But actually, that's what happened in our data set, and applying this technique to more different data set or large data set is going to be our future work.
Right. What is not clear there is that you are actually fuzzing any program that has already been like significantly fuzzed. right? Because if you get a new program, you're always going to find bugs. But the question is like whether you get a program that has already been applied with other techniques, and something like mutational fuzzing is still going to be able to find bugs that weren't found before by other techniques.
Can you repeat the last?
So, I mean, it's not clear that the programs that you actually have in your data set, they've already been fuzzed with other non-mutational techniques, right? So that would actually be very good. If you are actually able to find that you can find new bugs with a simple technique on programs that actually you've applied more complex techniques, then that would definitely demonstrate it. But these programs is not clear that has been done.
I guess, okay, so it's not, so you're saying it's not clear whether this program is representative. Is that what you're asking?
Right, in some sense, yes.
Okay, so sure. So this program is actually, as I said, we obtained this set of programs from one of our previous work. And the reason why we selected this program is because we know that we can crush this program and we can collect the ground truth data. And that was the main reason why we chose this program. And for that reason, we actually opened our source code and data set for further research, so people can use our data set and code to apply this technique for other programs as well.
Okay,
Thank you.
Thanks, Kil, again. And